Good morning, students. This is Satishkumar. In this video lecture, I'm going to present the work done in an electric field. So here, I am taking a positive charge plus Q, which is actually creating the electric field uniformly in all the directions. Okay, so everywhere the electric field is coming out radially outwards. We can say this is the direction of the electric field for this particular line, and this is how the electric field is leaving here. So this is the electric field direction everywhere is radially going outwards, which we can say AR vector. Now, in this electric field, let us try to bring a test charge. Let us call that is QT. If you bring that test charge and keep it exactly on this spherical surface, which is an imaginary surface, everywhere the electric field is same because the distance will be same. If you bring the test charge QT on this and if you place it, definitely this test charge is going to experience some kind of repulsive force because this test charge is also a positive charge and this is also a positive charge which is creating the particular electric field. So now there is a repulsive force between this Q and the test charge. That means this charge Q which is creating the field is exerting some force on QT, as well as this QT will also exert force on this Q which is creating the field. Now we will try to find out the force exerted by this charge Q on this test charge QT first. Okay, so first in this work done, let Q be a point charge which is creating the electric field. Point charge which is creating the electric field. E. Right. Now the charge QT which is the test charge, let a test charge QT is brought near the electric field, or we can say the charge Q. Anything is fine. Right. Now the point is, what is the amount of force that this Q is exerting on the test charge? Let us try to find out that force. What is the amount of force that Q is exerting or applying on test charge QT, How do we get this? To get this, we have to use the concept of electric field intensity. Okay, when you use the same kind of diagram for finding out the electric field intensity, we have got the expression for electric field intensity as we know that the electric field intensity E vector is equal to this is the force applied or exerted on a unit test charge. This their QT we have taken it as 1 coulomb of test charge. That is a force exerted on a 1 coulomb of test charge is defined as the electric field intensity. From this, it's very clear that what we'll be getting is the force applied by the electric field on this test charge will be absolutely equal to, it is a simple cross multiplication, F is equal to E vector into QT. This is what is the force exerted by the charge Q on this test charge QT. It's a very simple relation that we are getting in terms of E and QT, where E is actually Q by 4 pi epsilon r square AR vector. That means if you simply substitute this E vector here, this is Q into QT by 4 pi epsilon r square AR vector. That is nothing but Coulomb's law, which is the force between the 2 point charges Q and QT. Okay, we have not done anything new, which what we have done is from Coulomb's law itself. Now, what happens when the charge Q is applying force on this test charge? What happens here is, because this test charge may be a very small charge and this charge is a very big charge, when this charge is applying force on this test charge will absolutely move in the same direction of line joining, because the statement of Coulomb's law itself is saying that the force between 2 point charges is directly proportional to the product of charges and inversely proportional to the square of the distance, and the force always acts along the line joining the 2 point charges. So what here we'll be doing is, I'll be just extending this particular line a little bit. Let us call this is now the new position of the point charge, Now we can say this test charge is no more here. This is now the new position of the test charge, which is moving, let's say, in this direction by a distance dl. dl is a vector there because this point and this point are there in a rectangular coordinate system, or you can say spherical coordinate system. So obviously dl here will be a vector quantity. Now this is the new position of the test charge. I want to bring this test charge back into the same position, that is to get the equilibrium. We have to bring this test charge QT back into the same position. So what will be the amount of force that is required to bring this test charge back into the same position? So what we can write here is, to bring to have equilibrium condition. Equilibrium condition means the total force at a point will be equal to 0. To have the equilibrium condition, we have to bring the test charge back into the same position. That is, let us now move this test charge back into the same position and place it again back into the same place. How much amount of force that is required to move this test charge back into the same position? But here the problem is, this is the direction of the electric field. That is moving in this direction. Whenever you are moving a charge in the direction of the electric field, you are not moving this charge, you are moving this charge, and this is the direction of the electric field. Whenever in any particular field, if you try to move something, you don't require any force, or you no need to do any work done in that particular direction. Let us take, for example, if you try to drop something from a height of, let's say, some 1 meter or 2 meter above the earth, if you just release it, what happens is it will just simply fall down. That is because the gravitational field is acting downwards, which is having a acceleration due to gravity, which is 9.8 meter per second square. That means when you drop something, you no need to do any work, you just need to release it. The remaining force applied and the work done is by the gravitational field itself. That means in the direction of any particular field, we no need to do any work. But if you try to lift that particular one which you have dropped, definitely you need to bend down and you need to lift it by applying some force. That means whenever you are doing anything which is against the electric field, definitely we, the external person, should apply some force and have to do some work, because work done is the force applied on some body to move some displacement or distance. Okay, so this is what we have to first understand. So here, to move this particular test charge qt, which is actually in this direction, which is opposite to the field direction, because field direction is in this direction which I have shown, but now you are moving a test charge which is exactly opposite to the field direction. So whenever you are doing any force, or whenever you are applying any force which is opposite to the field direction, definitely some external source has to come into the picture. So this particular force is applied by some external source. That means the external source here is doing the work. That is what is this work done is. So here we are not going to find out the work done by the electric field. We are going to do the work done by the external source, because the charge, test charge, has to be moved against the electric field. The external source should come into the picture and should do the work. But how much amount of that external source has to apply on this test charge to bring that particular charge into the same position? This is same as the amount of force that the electric field has applied on the test charge to move from this position to the position which is now the current position. But this force applied by the electric field and the force applied by the external source must be in opposite direction, because in this direction electric field is applying, but the external source is exactly applying in the reverse direction. Both are having the same magnitude but in opposite direction. So we simply need to write the force applied by the force applied by the external source. The force applied by the external source is equal and opposite, equal and opposite to the force applied by the electric field, let's say E. And that force applied by the external source is, let's say, denoted by FA. A here represents applied, external. Okay, we don't denote it with E because FE actually represents electric field. That's the reason I'm not representing with FE. Let us denote it by FA, which is equal and opposite to the force applied by the electric field. So EQT is the force applied by the electric field, and minus E into QT will be the force applied by the external source. I'm calling this as second equation. Almost we have come to the end of the expression for the work done by the external source. Now, this is only the work done. Sorry, this is only the applied force. From this, we have to find out the work done by the external source. So this is the starting point. This is the starting point of the test charge, and this is the final point of the test charge after moving by the external field. Now the point is, this is a very small distance which is a dl vector. The amount of work done here is also a very small work done, so we can call that is simply the differential work done. We can simply call that is a differential work done, by the external source, by the external source. is, let us denote that differential work done by dW. Work done is always equal to the force applied on a body to move a displacement of, let's say, S. And we know that very well as that work done is always equal to F vector dot S vector. This is what we have studied already in our 12th standard. And this work done is a scalar quantity, F is a vector and displacement is a vector. When this displacement is a distance, this will become simply F into S, because work is also a, sorry, force is also magnitude and S is simply a scalar quantity. We simply need to multiply to get this work done, which is a scalar. But whenever they are vectors, you have to take the dot product between them. But what is the force here? Fa. And what is this displacement here? It is dl, okay, which is a displacement. So we can take that as simply Fa vector dot product with the displacement here is the dl, which is either in the forward direction or reverse direction. We, that will be same, because the same displacement moved by the electric field and the same displacement is also moved by the external source. The displacement is dl here, and Fa dot dl will be our expression. Now from this what we get is Fa is very clear, that is the force applied by the external source, which is equal to minus E vector into Qt dot product with dl. But this is a differential work done. This is a differential work done. To get the total work done, what we have to do is we have to take the line integration. Then the total work done will be, the total work done will be by taking the integration on both sides, which is a line integration, because it's in the form of a line. So or else we can say we have d Fa dot dl, which is a differential length, so we have to take line integration. Now minus we have qt into E vector dot dl vector, and minus qt is just a constant, we can bring that out, and therefore the total work done W will always be equal to minus qt, you can bring outside, line integral E vector dot dl vector. But what are the limits of this integration? Okay, from what to what? What is the lower limit value and what is the upper limit value? So here, the lower limit will be the starting point of the charge where you are moving. This Q2 is moving from this particular place, and it is the final value. So we can simply call this is initial, let us denote it by in, and this is final. Or else we can say this is denoted by b. I'm indicating this with b, I'm indicating this with a. In some textbooks they'll represent this as a and this as b. It's our denotion, our wish. Okay, we am representing here with b and here with a. Just follow the instruction till the end of the entire derivations, which are based on the work done. So this is b and this is a. Okay, so the initial location is B and final location is A. So what we can now write this is the initial location B and the final location A. And the units of work done will be joules. And this is the expression for work done. By using this expression, we can able to find out to move a test charge in the direction and also opposite direction of the electric field. We can able to get this by using the same expression, that the work done, we can able to get the work done by the electric field as well as work done by the external source. How that is possible, we are going to see in the properties of work done. Okay, so in the properties of work done, we'll be seeing in the next lecture. I hope everybody understood this. If you like these videos, please subscribe my channel. Thank you.